Hi, hello everyone. Good evening. Hello and welcome all of you today with a new webinar with Embedded Meetup. Today's webinar will be about OSEK and RTOS Internals. And our speaker today is an engineer with a great experience in the field of AutoSAR OS and RTOS and OSEK and all these stuffs. Our speaker today is Sarea. Hello, Sarea. Hello,
Hi,
Sarea. How are you?
hi, Mackie. Fine, thanks for
Hi.
asking. What about you?
Great. So, what are you preparing for us today?
Yeah, actually, it's like a quick introduction to AutoSAR operating system or OSIC operating system.
Yeah, okay.
Yeah,
That sounds very good. Okay, so would you like to give our audience an introduction about yourself and start your presentation?
okay, sure.
Okay, great.
Let me start.
Thanks.
Yeah. Is it visible, Majdi?
Yeah, I think yes. So
Okay,
I would like also, sorry for interrupting you, sorry about.
sure. Yeah.
For our audience, if you have any questions, just place it in the comments in YouTube. And if you have any issues like with the voice or anything else, just raise a flag inside the comments. Thanks. The mic is with you. Sorry.
Yeah, thanks, Majdi. Big thanks for you guys for Embedded Meetup for hosting me for such a great opportunity to share some knowledge about the operating system in automotive industry, and I hope it will be a good one. This is Sari Alhariri. I am a software engineer. I have been working in the industry for many years, around 5 years. I worked into different systems from ADAS to, driving assistance system to powertrain systems and others. And yeah, I guess that's it. And I will start right now. Majdi, can you confirm if something is shared or if you are seeing my screen? Is it visible?
Yeah, I can see it.
Okay.
And also for our audience, if you have any issues, just please raise a flag.
Okay, sure. Thanks.
Thanks.
Okay, now, yeah. First off, yeah, this material is always incomplete and it might be corrected or improved. So for any fix or correction or any feedback, just drop a mail or message me directly. Our agenda for today is like quick introduction to the operating system, and the next point is the task management in OSIC environment, and then the event management. After that, we will discuss the alarms and counters, which the which is the OS object that can be used in order to handle the recurring events and something like that. Then we will talk about the scalability classes of the operating system, resource management, and the ISR. Maybe in the next sessions or in the next webinars, we can talk about the safety and hook routines and some other parts that are not covered here. Okay. Historical background, OSIC standard is designed for a reliable software architecture as a standard, and it should be used, or it was designed to be used into different ECUs. So um, I mean, like the OSIC standard can be used. I saw that OS and I saw that module into different systems, like powertrain system, for example, the driving assistance as well, and so on. Um, in 1993, it was founded by mainly BMW, Bosch, Opel, Daimler, and Chrysler, and VW Group. It was standardized in under the ISO 17356 into 6 different parts, including the operating system, communication, and network management, and so on. And in AUTOSAR first version, 2003, it was reused, or the OSEK specs was reused by AUTOSAR standard, and the AUTOSAR standard covered some missing or gaps in the OSEK specs and add some other features related to the safety and schedule tables, and supported the multi-core systems and so on. And now I will talk something about a little bit about the definitions and terminologies. First off, we will talk about later on. We will talk about the conformance classes in details, but for now, I just wanted to say something about the scalability. Scalability means we say the OSEK is a scalable standard or scalable operating system kernel, means that the different capabilities of the operating system can be scaled. So you can switch on or off the capabilities of the operating system to support different systems and different features. The next one is the static configuration or statically configurable operating system, and which means let's say I have, for example, here in the code snippet, we have the static configuration of the operating system, means like specific parameters and specific containers should be configured in the operating system. For example, the stack size of a specific task or a specific thread can be configured in a specific GUI, and then the GUI will be used in order to set or write or provide the XML description or the OIL description. And then that system description or the OSEK implementation language file stands for, the OIL stands for OSEK implementation language, will include that description. And then we say there is a system generator that will use that description in the XML description or the OIL description in order to generate a C code that will be compiled in addition to the application software in order to be there in the final executable file. In that example here on the right, we are setting the stack size of task A, which is assumed to be application task, to be 100. And after configuring that, the system generation step, which will be the next point here, will be done. And the output of that step will be the OS configuration output file, and that, what we call it, the generated code. Now, the rest of the code is the static code, means it's written one time, it's not generated, it's not being modified by the configuration and so on, but it will reference the symbols from the generated code based on the configuration. Now the operating system is having a scheduler with fixed priority, so it's not expected to change the priority levels of different threads during the runtime. And the next terminology is the scheduling point, which is a point in time, specific point in the execution at which the scheduler entity will be triggered and executed. And then the scheduler responsibility is to choose the highest priority level in the ready task or in the ready queue, and then move it to the running state and jump back to the application. Okay. Now let's start with the first topic, the task. And let me remind you guys that the task, and in some other textbook, they are saying process or thread. All of this, I mean, they are referring to the same thing. The task is just a single sequence or sequential flow of programming instructions that can be executed under the processor or by the processor. And each task or each thread uh, theoretically has its own memory, which is the stack, and its own the question. Okay, its own set of registers. And the task will be, once the task is running, it will pop the context and load that values from the registers into the CPU registers. And once the task is preempted or is moving out of the running state, then it will store these set of registers and store its own local data into the stack. Now, for sure, just like any other operating system, the task has a specific state machine. And in OSEK environment, we have two different types of tasks. The first one on the right is the basic task, which has three different states: the running state, the suspended state, and the ready state. Now, in the running state, the task should have the highest priority, and it's running, it's being executed, and there is no ready higher priority task. The task can be preempted, so it will go to the suspended state. It will never be scheduled. It will never be executed again unless we are activating the task explicitly by a system service or by an alarm. And we will talk about the alarm in details after some time. Now, in the ready state, the task is ready and all of the preconditions from the operating system perspective are achieved, but there is another task with higher priority level that is being running, so that the task will be ready once the running task is terminated or left or leaving the running state. Then the highest priority in the ready queue will be moved and started, and it will be in the running state. Now, that state machine for the basic task. And there is one more task type, which is the extended task. For sure, that is configurable. You can configure your task in the system, in the application, to be basic or to be extended, and that is a design choice. That is a design choice, actually. In the extended task, we have one more state, which is the waiting state, and the task is allowed to wait on specific events to be set by another thread in order to move. And if the event is set by some other task, then the task will be moved back to the ready. And if it's having the highest priority, then it will preempt the running task and go to the running state, and so on. So that is for the extended task. We have two types of tasks. The basic task has three states in its state machine: the running, suspended, and the ready state. But the extended task has one more state, which is the waiting state. In the operating system, mainly we have 4 system calls that are related to task management activities. And actually, we have some more, but they are not affecting the task management activities. They are some getters. Get the task of the ID of the running task, for example, and the state of a specific task ID, and so on. But when we are talking about the system calls or the operating system services that are provided in order to manipulate the task and the task management activities, then we have 4 different services. The first one is the activate task, which will be used in order to move the task from the suspended state into the ready state. And if the task has the highest priority, then it will be moved automatically by the operating system to the running state. And now the next one is the terminate task, which is allowed for the running task only. So you cannot terminate another task, but the running task can terminate itself only. That is allowed. And if that service is called, then the running task will be moved to suspended, and it will be never executed again unless it's being activated by the software, and accordingly it will be moved to the ready state and so on. Chain task, actually, it will be that service is having an input parameter. Chain task will activate the input parameter, the task ID that is provided as a first parameter, and it will terminate the current task. It's like executing activate task and terminate the current one in a single service, in a single call. And next is the schedule, which is the explicit call to the scheduler in order to be executed and check if there is a higher priority in the ready queue, and schedule that task and just move it to the running state. Now, these are the 4 different system calls that are related to the task management. Okay, if we have any question here, I can stop for a couple of seconds. And if there is no questions, I can keep going. Okay, I guess there is no question. Can we repeat the chain task? Okay. Okay, thanks, Khalid, for asking. Khalid is asking about the chain task. Chain task, mainly it has an input parameter, the task ID, and mainly the operating system will activate that ID that you are passing to the operating system by the first parameter, and it will terminate the calling task. Sorry, the caller task. I mean, the running task can chain another task, which means to terminate itself and activate the input parameter ID. Okay. Event management. Actually, the event, it's an OSEK object that can be used to achieve synchronization between different threads or different tasks. And mainly, it's like a binary flag that can be set or cleared, and events are assigned to tasks, which means they are not independent objects. So each task has its own list of specific events, and all of these stuff are configurable. So you can configure the list of events for each task in the system. Now, regarding the permissions, the owner task can wait for specific events, and it can get and clear its own events, while the other tasks can set specific events for that owner task. Now, the synchronization can be achieved like that graph here or sequence diagram here. Task A is running, and it will call set event, which is the first event service here. It will reference the ID of task B and the event ID. Now, the operating system responsibility is to check if task B is waiting for that specific event, and if task B has a higher priority level than task A, then task A will be preempted, and the execution will be in task B. Then task B will up and running, it will get the event, it will clear the event, and it will handle that event through executing uh, the functionality that is related to that specific event. The event management services that are provided by the OSEK operating system is the first one we talked about it. Set event, you are referring to the task ID, the owner task, and the specific event that you are trying to set. And it might be a scheduling point. So if the task ID here has a higher priority than and waiting for that specific event, then the running task will be preempted. The next, the service can be triggered or called by the owner task to get the event in order to know which event uh, is set by any other task in order to handle the functionality that is related to that specific event. The owner task can wait for specific event using wait event system call, and based on that, if that service is triggered, then if the event is not set previously by any other task, then the task will be moved to the waiting state. Now, after handling that event, the owner task will clear that specific event in order to be notified in the next time when the event is being set. Okay. Um, Now we will talk something about the preemptability. Let me remind you that we have two different types of schedulers. The preemptive one, when the task can be preempted by the operating system or by the scheduler anytime in order to execute another task because it has a higher priority level than the running task. So we call that a preemptive scheduler. And the next one is the non-preemptive. Some textbooks might call that cooperative scheduler or cooperative system, when the task itself can only leave the processor and allow another task to be scheduled and executed. So the task itself can terminate itself, but the scheduler is not able to preempt the running task. Now, these are the types of, the types of schedulers: preemptive and non-preemptive, or preemptive and cooperative. The point in OSEK operating system is like describing, instead of describing the scheduler itself to be preemptive or cooperative, we will describe or configure the task itself to be preemptive or non-preemptive. Now, the attribute, the preemptability, if I can say, the preemptability attribute is related to the task, not related to the scheduler. Okay? Now, based on that, we will be able to configure each task in the system to be preemptable or preemptive, or we can configure it to be non-preemptable task, so it cannot be preempted by the scheduler or by the operating system. Now, in this quick example, just to clarify that point, we have three different tasks: task A, B, and C. And task A is the lowest priority level, B is the mid priority level, while C is the highest one. First, we have B and C are suspended, so both of them are not running, both of them are not ready, and task A is running. And at this point, task A is triggering activate task system call. The input parameter is task B. Now, if task B is a non-preemptive task, then even if it's having a higher priority level than the running task, which is task A, it will never preempt task A because task A is non-preemptive. So it will just be moved to the ready state instead of running, and the preemptable, task A will keep running till the schedule service is being triggered or being called. In that case, task A is executing or triggering the scheduler explicitly by calling the schedule service, and then the operating system or the scheduler entity will be running. Then it will check the highest priority in the ready state, which is task B. It will be moved to the running state, and task A will be ready, and so on. Now let's check the difference here. Task B is activating task C, and both of them are full preemptive or a preemptable task. So task C has a higher priority level than task B. And bear in mind that task B is preemptable task, then it will be preempted after this call, and the scheduler will choose task C, and task C will preempt task B. Then B will go to the ready state, and C will be up and running, and so on. Based on the previous discussion here, we might have three different scheduling policies in OSEK operating system or in AutoSAR operating system. Now, if all of the tasks in the system are full preemptive tasks, then we will have a full preemptive scheduler or full preemptive system. If all of the tasks are non-preemptive, then we will have a cooperative scheduler, and the operating system will never preempt any task. The task only can terminate itself to let any other task to be up and running and executed. And the third scheduling policy, which is the most common, I guess, according to my experience, which is the mixed scheduling system. When you have a set of tasks are non-preemptable, and another set of tasks that are preemptive tasks. So in that case, the scheduling points will depend on the running task if it's preemptable or non-preemptable. Now, of course, each of the scheduling systems or scheduling policies will have its own scheduling point. So here, for example, the scheduling points in task termination or waiting request, executing wait event for extended task. These are scheduling points regardless of the scheduling policy. So both of them will trigger a scheduling point even if we are mixed, full, or non-preemptive schedulers. In the full preemptive system, the activation of another task is a scheduling point. Setting an event for another task is a scheduling point. Then releasing the resource and returning from category 2 interrupt is also a scheduling point. We will talk about the resource and interrupt handling after some slides. But if the system is non-preemptive, or if the current task is non-preemptable or non-preemptive task, in that case, the explicit call to the scheduler will be considered as a scheduling point along with the task termination and waiting point or waiting request, which means the waiting or wait event system call. So in summary, if we are in task that is configured to be preemptive, then we have the first two scheduling points and the full preemptive scheduling points. And if it's a non-preemptable task, if the task is configured to be non-preemptive, then we will have the first two scheduling points, and the explicit call to the scheduler will trigger a scheduling point as well. But the full preemptive scheduling points will not be considered at the runtime. Okay. That is a quick example in order to show the runtime behavior of the operating system if we are setting an event from a non-preemptive task or in non-preemptive scheduling system. Here in this example, we have T1 is an extended task, and it's having the higher priority, while T2 is running and it's uh, it's having the low priority. Now T1 is waiting for uh, that specific event here. The event initially is cleared. T1 is running. At this point, T1 is setting an event for T. Sorry, T2 is setting an event for task ID T1, and that specific event will be set, and accordingly, the task will be ready because T1 is waiting for that specific event. And then, even if T1 is having a higher priority level and it's in the ready state, T2 will keep executing because T2 is non-preemptible task until the rescheduling request here is being triggered, which is the schedule system call. And in that case, the scheduler will be executed. It will choose the highest priority ready task, and it will be moved to the running state. And then here we have T1 is clearing the event, running, and waiting one more time for the specific event. It will be moved then to the waiting state. And after that, T2 will be continuing the execution because it's only the ready task in the system. Now, the basic idea here is like even if T2 is setting an event for T1 and T1 is having a higher priority task and waiting for that specific event, the scheduler will keep T2 task, the running task, in the running state, and it will never execute T1 unless you are explicitly requesting or triggering the scheduler to be executed to choose T1 or the highest ready task to move it to the running state. Okay, if we have any questions, we can take some questions. Otherwise, we can move on. Okay. You might be wondering how are we handling the repeated actions or the periodic actions or the periodic task and so on. The answer is using the alarm, and the alarm OS objects along with the counter OS objects are specifically designed for that functionality, where we have two level concept, the counter, the OS counter, and the OS alarm object. Now the counter is just a simple counter represented by its own value. It will be increased each tick starting from the minimum, for example, which will be 0 here, to the maximum as according to the configuration of that specific counter, and then it will be overflowing and it will start again from 0 and so on. The alarm object is configured statically in the operating system, and it will be attached to the specific counter that will be used in order to compare if the counter is if the counter is reaching the maximum, then the alarm will be fired, and if the alarm is fired, then the alarm action will be executed. Now, what is alarm action? Simply speaking, the alarm action is one of three different options. It can be used to trigger a callback. It can be used to activate a task, and accordingly, you will have a periodic task if the alarm is cyclic alarm. I mean, if the alarm is being triggered cyclically, and it might be setting an event. That is the alarm action. So the main idea here is like we have the first level is the counter that will be increased till the maximum and then start over and over again from zero to the maximum and so on. And the operating system responsibility is to check if the current value of the counter is reaching the threshold that is configured for this specific alarm. And if so, then the alarm will be fired. And if the alarm is being fired, the operating system responsibility here is to execute the alarm action, which could be a callback, task activation, or event setting. And of course, in each choice here, you have to configure the ID. For example, like you have to configure in the operating system the callback name. In the task activation, you have to provide the task ID. And in event setting action, you have to provide the owner task, the task ID, and the event that should be set for that specific task upon the alarm firing. Okay, now let's have a quick look to the uh, alarm management services that are provided by the operating system. First off, set relative alarm. The input parameters are the ID of the alarm and the increase value, then the cycle value. And in that case, uh, the alarm ID referenced here in the first parameter will be fired after the increase value from the current point in time, and relative to that fire after the cycle, it will be fired in a periodic manner, I mean. The next service is setting the alarm in absolute mode, set absolute alarm. And in that case, that alarm ID will be triggered when the equivalent counter, when the base counter of that alarm is matching exactly the start value here. And after that, relative to that point, after the cyclic, after the cycle value provided here in a periodic behavior. Now, of course, if the alarm is being uh, running, if the state of the alarm is running, then you can cancel that alarm if it's not needed anymore. And you can get anytime the tech reference, which is the value of the base counter of a specific alarm that is referenced here in the first parameter. Okay. Now, in order to understand how exactly we are handling the relative behavior uh, and the absolute behavior of the alarms, here we have, in this example, we have that graph that is representing the base counter of the alarm that we are talking about. And the counter will be starting from zero till the maximum according to the configured value, the maximum of the counter. And after the maximum, it will be started again from zero and so on. At this point of time, the software that is running on the operating system is calling set relative alarm, providing the three different parameters, the alarm ID, the increase value, and the cycle value. Now, as that mode is relative, then the operating system will start measuring the number of ticks that are required starting from the current value of the equivalent counter. So after the current value from here, after the current value of that counter, of the base counter, by inc number of ticks, that is the first firing of the alarm. And after that, relative to that point, the operating system will measure the cycle number of ticks that is provided here to execute the next firing points. And after one cycle, it will execute the next firing points and so on and so forth. The main idea here is like the first firing point of that alarm will be measured or will be considered relative to the current value of the base counter of the referenced alarm ID. Now let's check the next behavior, the absolute one. If we are setting that alarm in absolute mode, the software at this point of time, when the counter value, let's say, um, 10, for example, the software that is being run is requesting set absolute alarm, and it's providing the ID, the start, and the cycle value as input parameters. And now the operating system will check once the equivalent counter is equal exactly the start value, then that is the first firing of the equivalent alarm, not relative to the current value, but it will be considered as absolute value once the counter value is equal to the start provided value here. Then the alarm will be started, the first fire of the alarm will be executed, and the alarm action will be handled here by the operating system to call the callback or to activate the task or to set the event according to the configured alarm action. And after the first firing by a cycle, it will be the second firing, and after that by one more cycle, it will be firing the next action, and so on. Now, for sure, you can provide the cycle as 0, and it will be one shot alarm. It will be triggered for one time. The alarm action will be fired one time, and then the alarm will be disabled automatically. And if it's required one more time, you have to require or to call that service that is provided by the operating system. Okay. Yeah. Now, when we started that session, we say that the operating system is scalable, and we talked about scalability. Actually, this means that the okay, I will keep the questions till the end of the session. Maybe that is better for some of the audience. Good. Okay. Okay. Now the scalability classes. We have 4 different scalability classes in OSEK operating system: BCC1, BCC2, and ECC1 and ECC2. Actually, in BCC1 scalability class, the basic task only is supported, which means you are not allowed to configure an extended task or to configure a specific event for any task when you are configuring the operating system. And in that case, you are allowed to set single priority level per task. You are not allowed to provide more than one task per priority level, and it's not allowed as well to provide multiple activation in the software. I mean, if you are activating a task during the runtime, the next activation request will be rejected by the operating system, and an error code will be returned unless the first instance of that task is being handled and executed. According to that graph, for example, here in ECC2, now basic task is supported, extended task is supported as well, so you are allowed to set an event during the runtime and to configure the task to be extended, to configure a list of events for each task, and so on. And you are allowed to set more than one task per priority level, and the operating system will service these different priorities if all of them are ready in the same order. So the task that is having the same priority level, if it's activated first, then it will be handled first and executed first by the operating system. It's like first come, first serve for that priority level only. And you are allowed to activate the task multiple times by the by the software, which means the operating system will queue the different activation request. And if you are activating, for example, the task 3 times, then the operating system responsibility is to execute that task 3 times as well. Okay. Now we will move to the resource management. In resource management here, let me remind you first about an old problem in the software, which is the racing or the data inconsistency. In any multi-threaded system, we have more than one task or thread, task or interrupt, and each task is having its own private data. Now let's have this example. Task A is running, sorry, task B here is running, and it's trying to modify the X variable and stored in the RAM. So it will load that variable to the task B stack. Now we have X star, which is the version of X that is related to task B. And before modifying that variable, before modifying and storing the X variable back to the RAM again, the task B, task B here is preempted by task A, and task A is loading X. So we have X dash added by 2. Then we will store, after modifying that X variable, we will store that again to the RAM. So here we have the RAM version of X will be 7 after adding to the number by 2. Here we have 7, and then here at this point task A is terminated or uh, moved to the waiting state, and task B is running. Then it will return exactly to the same location leave from where it leaves the processor. It will modify the version, the private version of X, which was 5. It will be moved to, it will be modified to 6, and then it will store it back to the RAM. So X will be updated to 6. In that case, task A is thinking that the RAM variable is 7, but task B is considering that variable to be 6. That is the data inconsistency or racing conditions problem. You might be aware of the resolution of that problem in the software. The mutex or semaphore, which is like a binary flag that should be locked or taken before and released or unlocked after accessing the shared data. So here, for example, task A is running. At this point, task A is getting that resource or locking the semaphore or mutex. And at this point, task B is running. It's preempting task A. So A will go to the ready state. B is running. At this point, B is trying to access that shared buffer, but it will be blocked on that because the buffer or the resource is already locked by the previous task, which is task A. And now the operating system will block the second task and run the first task, which is task A. And at this point, task A is releasing or unlocking that shared resource, and the operating system will unblock task B and move it to the running state while task A will be in the ready state. That is the common resolution. However, it has two different drawbacks. The first is the unbounded priority inversion, when the lower priority task is blocking a higher priority task. And then the next problem is the deadlock, when each task is waiting for the other task in order to unlock the shared resource. In this example, T1 is running and T2 is ready, and T1 is locking semaphore S1, and then at this point it will be moved to the waiting state. Now the operating system will run the ready task, which is T2 task, and now T2 is running. At this point, T2 is trying to lock the second semaphore S2, and S2 is unlocked, so it will be locked by task 2. Then at this point, task 1 is getting ready, so it has the higher priority level, so the operating system will move that task to the running state. And at this point, the problem is coming. Task 1 is trying to access semaphore 2, which was locked by task 2. So it will be blocked or waiting for that specific mutex or semaphore in order to be unlocked, and the execution will be back to the second task. Now task 2 is running, and at this point it's trying to lock S1 semaphore, which was locked previously here by task 2. Now task 2 is waiting, task 1 is waiting, and the system is uh, in failure mode. T1 is waiting for a specific resource that is locked by T2, and T2 is waiting for a specific resource that is locked by T1. That is the deadlock problem. Now, in order to achieve the data inconsistency resolution and the racing problem, the critical sectioning uh, behavior by the operating system, and in order to avoid such problems, deadlocks and priority inversion, OSEK is providing the priority ceiling protocol or priority ceiling pattern, which will be used in order to uh, get rid of racing problem, and at the same time it will never fail in deadlock or priority inversion issues. Okay, here let's have a quick example. First, the priority level will be assigned to the resource itself, which will be called the ceiling priority. So if we have a shared resource, we will assign a specific priority level to that resource, not to the task. And the resource ceiling priority will be higher than the highest priority of the user task. And at the same time, it should be lower than the lowest priority non-user. In that example, here we have 5 different tasks from A to E, and we are having B and C, both of them are configured to use that specific resource. So we have B with priority level 15, C with priority level configured to be 20, and we are considering to calculate the ceiling priority of that shared resource. So we have B and C are resource users, and the higher priority is 20. So the resource priority should be more than or equal to 20. And at the same time, if we have a non-user task like A, D, or E, and at the same time it's having a priority level more than C, more than the highest priority user task, then we have to assign the priority of the ceiling level to be less than the non-user highest priority task. In that case, in that example, we will have to provide the assign, we will have to assign the ceiling priority to be more than 20 because that is the highest user priority, and less than 30 because that is the non-user task that is having a higher priority level than the highest user task. Maybe that is complex a little bit. In that case, we will have the ceiling priority to be between 20 and, sorry, 27, not 30, because 27 is the least one. That is more than 20 in non-user tasks. Now, what will happen in the at the runtime is something like the following. Here in that example, we have 4 different tasks, and task 4 is running. Task 1 is the highest priority. After that, task 2 is the next higher priority, and then task 3, and the least priority is task 4. And we have a shared resource represented here in that bar, and T4 is running. While it's being run, it's requiring the resource. The minimum priority task 4 is requesting that resource. In that case, the operating system will change internally the priority level of task 4 to be equal to the ceiling priority of the shared resource that we are requiring here. So it will be moved and running at that priority level, which is the ceiling priority level, which is more than the different priority levels of the user tasks. Then at this point in time, we are getting preempted. Task 4 is getting preempted by task 0, which will not use the resource and is having a higher priority level than the ceiling priority. So T4 is running, and then T4 is suspended. So the control will be back to the task 4, and it will keep continuing and executing its own code at the ceiling priority level. Once the release resource is executed by the operating system, once the task is releasing that resource and locking that resource, then the operating system will change the priority of T4 back to the original or to the home priority according to the configured priority level. So the task will be moved back to the ready, and here we are having task 1, 2, 3 were activated in the middle here. So the operating system will check the highest priority level, move it to the running state, and then it will be executed. If it's requiring the resource here, the operating system will move it to the ceiling priority level. And once the resource is being released, then the task priority will be moved back to the home priority till the task is suspended. Then the operating system will get the next priority level, the highest priority level in the ready state, and it will be running. Then T3 will be running after termination of T2. Then after the termination of T3, T4 will be up and running again as the minimum priority in the system. The main idea here is when a specific thread is requesting a resource, it will never leave the processor to any other task that might take the same processor, even indirectly. So it will keep running till it releases the resource, or if a higher priority task is being triggered or activated, if that task will not request that specific resource or shared resource. Okay, now that is the priority ceiling protocol, and we still have one last point. Okay, here in the ISR handling in the operating system, we have two different types of task. We have, two different types of ISR, category 1 and category 2 interrupts. Now, category 1 interrupt is just like any interrupt you might know. It will be just like any hardware event, can message, for example, or a button on the ECU or on the board or something like that. The hardware event will trigger the interrupt service routine to be executed in the processor, and the interrupt service routine will interrupt the running thread, even if that was the operating system or an application task or anything. Once the operating system, once the ISR is done, it will the control or the execution of the software will be back to the exact location where the interrupt was triggered. So the task will be continuing its own code. In that case, we are not providing a supervision by the kernel. For example, the stack protection system calls are not allowed. So in that interrupt, you are not allowed to manipulate or change or request any system call that might change the task management activities, because the operating system is not aware of the execution of that interrupt service routine. And after the routine is done, it will return to the same exact location from where the execution of the task was left. So the task that left the processor, or the task that interrupted by the ISR, it will be continuing its own execution from the exact location. Now, the idea here is like we are having we have another category, which is category 2 interrupt, and in that case, the interrupt will be supervised by the kernel or by the operating system. So once the interrupt is being triggered, the operating system will prepare or allocate a specific stack size for that category to interrupt according to the configured values. If we are applying any timing protection, it will be applied to that ISR as well. So generally speaking, the operating system will be as a supervisor to that interrupt. For sure, in that case, the operating system will allow you to call or to request the system call. So you are allowed inside category 2 interrupts to execute system call services, or change the task management, for example, or to activate a specific task or something like that. And after the ISR is done, in that case, the operating system responsibility here is to return to the correct task, to the proper task. So if you are activating another task, it may or may not return to the task that was interrupted before the interrupt, in case of category 2 interrupts. This is a quick example. Here I have task A related to the application. It's being executed. At this point, there is a hardware event that happened, and based on that, by hardware, the execution will be moved to the ISR. Then the interrupt service routine here will be executed. Once the ISR is done, the execution will be back to the same task and to the exact location where the task was interrupted. As you see here, the operating system is not aware, and there is no supervision. There is no scheduling point while returning. There is nothing provided by the operating system, and you are not allowed to change the task state or to set a specific events, for example, or to activate a task and so on. See, most of the system calls will not be allowed here. The next category 2 interrupt, on the other hand, here we are having task A is being executed and the interrupt is triggered here. Instead of moving directly to the ISR provided by the user or provided by the system integrator, the execution will be moved to the operating system. Now, the operating system will check the context here if the task is preemptible and if, in case the previous context was interrupt, then the operating system will compare the priority levels. And if all of the checks provided by the operating system here are achieved, then the operating system will forward the execution to the ISR. Then the ISR will be executed, and inside here you are allowed to request most of the operating system services. And once the ISR is done, the execution will be back to the operating system, and the operating system will trigger a scheduling point, and it will be back to the same task or to another task depending on the task management changes that was that were requested here inside the ISR. In that graph here, for example, we are activating task B inside the ISR. So the execution will be back to the operating system. And after the operating system, the execution will not return back to the preempted task. Instead, the scheduling point will enforce the highest priority ready task, which is task B that was activated in the ISR to be running, and so on, so forth. Yeah, I guess that's it from my side. And if you have any question that I can answer, we can go ahead. Okay, I have a question. In the previous example, what if the task that already running not called the schedule module, the over task will stay in waiting forever? Okay. Uh, I might not be able to get back to the specific slide that you are asking, but generally speaking, if the running task is waiting for a specific event that is not set by anyone or by any alarm or any other task, and if there is no task from the application perspective ready and can be run, in that case, the responsibility of the operating system is to provide the idle mechanism called. The idle mechanism is just like a task that will be executed by the operating system if the application is not having any ready task. I hope that might answer your question. What is the application in real world for using relative alarm and absolute alarm? Actually, absolute alarm, I saw that to handle different periodic tasks. I saw that in different system. However, I don't have actually a real world example related to the uh, relative alarms. I don't know any use case actually for that.
I think if I have understood correctly, the question that is related for the task that will run forever, or sorry, will be waiting forever. I think it is related to the extended tasks. I think you mentioned that, or I think it was related to the cooperative system. I mean, non-preemptive systems. You mentioned that when a task has not finished, um, I mean, no one can interrupt this task till it decide by itself to leave the scheduling. Uh, I'm not sure if I have explained it correctly. Sorry, Saria. I think you are muted.
I'm sorry, Majdi. Yeah. Can you just tell me the question one more time?
Okay, so I think the question that is related to the tasks that will wait forever, I think it is related to the cooperative systems or non-preemptive tasks. You mentioned that if a task, a non-preemptive task, if it does not decide by itself to leave the scheduler, then no one can interrupt it.
Mhm.
So I think this is the main
Okay, the
uh,
task, yeah,
question here.
the task is not allowed to return like a regular function in C. Actually, that is strictly not allowed by the specs of the operating system. This is the first point. The second point, if the task is not preemptable, it will keep running until it's triggering or executing the uh, the scheduler explicitly, which means to call the schedule service provided by the OS. Now, if that is not happening, then the task should keep running, and in case there is a waiting point or waiting request, it will be moved to the waiting state while there is no other task in the ready state. And again, the operating system will move or will forward the execution to the idle task that is provided by the operating system as well. I'm not sure if that is a good answer or it. Yeah.
So I think if no further questions from your side, then I think it's fine for today. Or do you have anything else to present, Sammy?
Nothing from my side. Thanks a lot for attending the webinar, and thanks for you guys, embedded meetup, Majdi and other guys. Thanks a lot.
Yeah. Thanks, Sarah, for your time, and
Sure,
wait you for the next webinar.
sure.
Thanks, all of you.
Sure. Thanks a lot. Have a good
Thank
day.
you.
Sure.
You
Bye.
too, all. Bye.
Bye. Bye.